Welcome to Unit 14. We're halfway there in the last part of the semester and this interesting transition to online delivery of the course. So I hope you're all doing well, and we have one more chapter to go. We're going to cover this unit over 2 lessons. So in this first lesson, we're going to talk about some basic ideas of equilibrium, and then we'll move on to more advanced examples next time. So equilibrium can be divided into 2 parts. In this chapter, first we'll talk about equilibrium of a point body. So by a point body, we mean that the mass of the object is concentrated at a point. So we're not interested in considering things where the center of gravity is calculated. The center of gravity is the point itself. In this case, we're going to consider 2-dimensional equilibrium. So let's take a look at the following 2 conditions that we use for equilibrium. This operator here is the summation operator. It simply means the total. And in this case, it's saying that the total forces in the x direction and the total forces in the y direction have to be 0 if an object is to be in equilibrium. So the first 5 examples that we'll look at are very similar to examples that we looked at in the chapter on vectors. Alright, let's start with example 1 now. We have the following 1-dimensional diagram, and the question is to find the value of F, the force, so that this system is in equilibrium. If I was in your shoes, I'd probably answer it the same way, which is just to say it's 43.1 pounds to the left. But, and I'm not expecting anything more profound from you in a response. However, I do want to cover this example in a bit more rigorous way by looking at how we can use the formula. See, the net force in the x direction has to be 0. We can solve for F here, the vector F, by substituting the 2 quantities, the 2 vectors, into this equation and adding them up to be 0. So there's your vector F, that's unknown, and there is the known force, 43.1 pounds, to the right, and algebraically we can solve for the vector F. We simply move this term over to the other side, and a negative sign appears. This answer is correct, but it's a bit redundant to have a negative when you have a direction right. So we can take the negative and absorb it into the right direction, thus giving an answer of left. So you recover the exact same answer that your intuition and quick observation would have given you in the first place. Let's see the next example. In this example, we have a force that's directed upwards. The rest of the diagram is actually identical to the previous question. So you'll see that this analysis is the same as what we had earlier. But what about F2? Well, the left and right equilibrium are satisfied by that equation, and the up and down equilibrium, that is the net force in the vertical direction, must also be satisfied. Well, since there is no downward force here, then the upward force has to be 0 in order to preserve equilibrium. Or, if you want to, you can add up all the forces in the vertical direction and see that they indeed add up to 0. There is only one force in the vertical direction, so it by itself must be 0. In this third example, we extend and build on the previous example by adding a downward force. So now, how does this downward force change the answer? Well, the first part is identical to example 1 and 2, because the x direction, the forces are still in the same relation. However, in the y direction, we do have an extra term in this equation, right there. 35.6 pounds acting down. And if we take this term and move it to the other side, we'll get a negative sign, and that negative sign can be absorbed with the down to produce an answer of up direction. So there you have it. Equilibrium is satisfied by having F1 and F2 as follows. These examples are very straightforward, hopefully, and what makes them straightforward is that they are aligned to the vertical and horizontal directions. What would make an example more complex is if a force was, for example, at some angle, like this. And that is exactly what the next example will introduce. So how do we manage through this example? These vectors here are still the same as before, but we have this new force vector, which is angled at 28 degrees above the horizon to the right. So what does that do to the system with the equations here? Well, there's your x equilibrium and there's your y equilibrium. What this means is that we are going to add an extra term in the x direction right there and an extra term in the y direction. And those terms come from drawing a force triangle. You can use your basic components. That is a right angle triangle. There's 51.9 pounds and your 28 degrees. So the x component is found by using cosine, and the y component is found by using sine. And that's exactly what you see in the equation. So for example, there's the one term coming from the cosine component, and there is the other term coming from the sine component. Notice that I've included the directions up and right for the vertical and horizontal directions respectively. At this point, we have three terms, 1, 2, 3. If we take the two terms that have numerical values given and combine them into one term, we get that, 88.9 pounds to the right. That's pretty easy to do because both directions were right to begin with, so you're adding like terms. And to find the answer for vector F1, simply move this over to the other side, which gives you a negative sign, and that negative sign combined with the right turns the answer into left, which makes sense and is consistent with the diagram. Vector F1 is pointing to the left. In the vertical direction, a little bit extra care is required since we have a downward direction for this and an upward for that. We talked about in class how you can add them up quickly by first looking at which of the two numbers is larger. So which is larger here, the down component or the up component? And clearly it's the downward one. So the downward one is larger by a value of 11.2 pounds. Hence, we have a net of 11.2 pounds down for the known numerical terms. We can move this term over to the other side and get your negative sign, combined with the down, producing an answer of up. So these questions really do involve a lot of bookkeeping, but in general, they are very systematic. Equilibrium for a point body is a very familiar skill to you already, although you might not perceive it that way, because the work that we did in the vectors unit is very similar to what you're seeing here. You can refer to Blackboard for this next example. What I've done here is introduced an additional force acting to the left, and I've moved some other things around. I've made this for the known force go to the left here, and now F1 is this way and F2 is acting down. Anyway, you can see this solution on Blackboard, and if you're able to do a question like this for equilibrium for a point body, then I think you have this one in the bag. So let's move on to something a bit more interesting. Next we have equilibrium of a rigid body. A rigid body, in contrast to a point body, is a body that has a mass that is not concentrated at one point anymore. That is, the mass is spread out. So, for example, rigid bodies that we can look at in this course include trusses and beams. I think you would agree with me that a truss or a beam is not a single point. It is an object that is spread out in terms of its mass. So how do we know, or how do we calculate equilibrium and the forces involved with trusses and beams? That's what we're going to look at in the next series of examples. The equations that we're going to use for trusses and beams and for general equilibrium of rigid bodies look like what we had for a point body thus far. However, there's an additional equation regarding moment. That is, not only do the forces have to add up to 0 in both the x and y directions respectively, but also if you choose any point on this object, the net moment about that point should be 0. Because if the net moment was not 0, the object would rotate. And if an object's rotating, it's not stationary, which means it's not in equilibrium. For the remainder of this lesson, I'll consider 2 truss examples in detail, and then I will defer additional examples on trusses and beams to the next lecture to follow next week. Here's example 6. We have a truss, and a truss, as you can see here, is the collection of these 3 members and is supported by what is called a pin and a roller support. The diagrams for the forces that are involved when modeling pin and roller supports are given in the notes on Blackboard. So in summary of those notes, I'd like to quickly say that with the pin connection, here's the pin, let's call that point A, the reaction forces occur both in the horizontal and the vertical direction. The direction of these arrows is arbitrary because you could say that it goes to the right and your calculations might tell you it goes to the left. So don't worry about the direction of the arrows, just worry about that they exist both in the vertical and horizontal direction. And for B, the roller supports allow for movement in the horizontal. There is no obstruction in that regard. So there is only a vertical force opposing the structure in this context. So just remember, with rollers, 1 force, and with pins, 2 forces. With this in mind, we can look at the free body diagram or the force diagram and figure out eventually what the reaction forces are. So let's get those reaction forces. So we're looking to solve for 3 vectors here. Here is the free body diagram describing those reactions. Notice that because at point A we have a pin, I've drawn 2 reaction forces. To make life easy, I called them Rx and Ra. Over here at the roller support, I've only included 1 force as a reaction, which is called Rb. So now, how do we establish equilibrium? Well, if we were to do what we did earlier with point masses, we could look at the net force in the x and the net force in the y direction, respectively. Let's see how far that gets us first. In the x direction, I'm going to circle this 20 kilonewton force as well, just to have it on standby. In the x direction, which I'll highlight in yellow, you only have Rx. So there's not much going on there. And because there's only 1 force acting in that direction, and we saw this earlier in one of the previous examples, that x force has to be 0. Similarly, in the y direction, which I'll highlight in blue, we have a 20 kilonewton force as well as Ra and Rb. Now, I arbitrarily chose Ra and Rb to be upward, but you can see here that intuitively it makes sense to counteract the 20 kilonewton force, which is in between the two. In fact, you can quickly say that Ra and Rb are probably the same value, which they are, but we'll get to that in a minute. In this case, we notice that the net force in the y direction immediately tells us that whatever Ra and Rb are, their total is equal to 20 kilonewtons. So how do we actually calculate Ra and Rb? Because with this information alone, we cannot solve for Ra or Rb. In this case, we have symmetry, but in general, you don't have symmetry. That's why you need a third equation, which is the one that I introduced. The net moment about a point is 0. Actually, the net moment about any point is 0. So the key thing here is you need to create a third equation. So this is equation number 1 and number 2. You need a third equation by the sense of we have three variables to solve for. See, 1, 2, 3 variables. We can find the net moment about any point on this structure, and it should be 0. Because for equilibrium, the net forces and the net moments should be 0. I chose the moment about A. You could choose A, B, or C. It really doesn't matter which you choose. However, if you choose wisely, it's less work. And the reason I chose A is because there's two forces that are going through A. That means that the moments of those two forces about A is 0 because their lines of action are going right through A. So when we look at the net moment about A, we only have two terms. The moment generated by the 20 kilonewton force and the moment generated by the RB force, which is at 6 meters away. See, this 20 kilonewton force, it has a line of action right here, and that line of action by symmetry is 3 meters away from A. Also, this one is going to produce a clockwise moment, so negative. That's why you have the minus sign here. The RB force is going to produce a counterclockwise moment, or positive, and its line of action is 6 meters away from A. That's why you see the 6 here. So we can take this equation and immediately we can solve for RB. Once you have RB solved, then you can go back to equation number 2 here for the vertical components and say that RB is 10, they add up to 20, so RA has to also equal 10 kilonewtons. So there you have it. An analysis of a truss, your first truss possibly. Here is a second truss example in which an additional force is added and an additional member is added to the truss. I'd like to direct your attention first to the supports here. Notice on the left this time we have a roller, and on the right we have a pin. The force diagrams that relate to these supports are given on Blackboard. For a roller support, we mentioned earlier that we would have a single force acting in the vertical direction, and for the roller, for the pin I should say, we would have two forces acting. Now I just drew them arbitrarily like that, but what do you think? Do you think it makes sense for A to point up and B to point up as well? Or are they pointing down? Or is it one up and one down? I think it's clear though one of them does have to go down, because otherwise all of the forces in the vertical direction are moving upward. And if they're upward, then it's not going to be in equilibrium. If you're worried about that situation and how to set it up, you just have to assume one way, and if the answer is negative, don't throw your answer in the garbage. It just means your answer should have been the other way around, and a simple therefore statement would remedy that problem, where you would say, oops, should have been the other way, here's my answer. So same thing goes with the force here for the reaction at B. We notice that there's a 15 kilonewton force acting to the left. I'm pretty sure B acts to the right. So when I draw the force or free body diagram on the next slide, let's see how you would have approached it and if it compares to what I did. So here's my diagram. I ended up here in the diagram changing my mind and putting the reaction forces to act downward, because it seemed logical that at least one of them is acting downward. And since I didn't know which one it would be, at least, I made them both downward. Also, I made Rx to the right because I'm pretty sure that it has to go to the right, being that it is the only other force that could possibly counteract the 15 Newton force here. So, we have three equations for equilibrium: the net force in the x direction, the net force in the y direction, and the net moment about any point on the object here. I chose A, for example, should be 0. It doesn't matter in which order you explore or use these equations. So if you chose to deal with fx, then fy, and then the moment, it would still give you the same answer. It's just that your pathway algebraically would be different. So don't worry too much about that. If you like, I often will do this when I was a student. I'll draw 3 columns and I'll put each force here and do some math and just see where it leads me to. Anyway, let's get back to the example and not to worry too much about the algebra. Hopefully it's nothing compared to the algebra we did earlier in the calculus component of this course. In the x direction, there is only one force acting to the right and only one force acting to the left. So I think it's very quick to say that the reaction force in the x direction is 15 kilonewtons. So let's check off that answer there. And we can go to the y direction, for example, and say that, well, the 20 kilonewton force is acting in the upward direction, and assuming that RA and RB are acting in the downward direction, we get RA plus RB is 20 kilonewtons. We'll come back to that later. We need an additional equation because with 3 variables, see, 1, 2, 3 variables here, we need 3 equations, and equations that are not redundant. The moment equation gives us a third equation that is not redundant. What we can do here is say that the net moment about A should be 0. Here's A. Any forces whose lines of action go through A are not important for this calculation because they produce 0 moment. So let me highlight the forces that are going to produce a non-zero moment about A. There's the 21 here, the 15 here, and RB here. And that's exactly what you see here. 20, 15, and RB. If you can figure out what their line of actions are with respect to A, how far away they are, then you're ready to finish this question. So let's talk about the 20. The 20 kilonewton force, by symmetry we mentioned earlier, is 3 meters away from A. There's the 3. The 15 kilonewton force, right here, its line of action is 5 meters away. That's 5. So there's the 5. If you don't mind, I'm just writing it over. It looks nice too. RB, well, RB is 6 meters away because there's its line of action. So there's your 6. Also, make sure you pay attention to plus and minus signs. RB relative to A will produce a clockwise moment. That's negative. There's the negative sign. This 20 kilonewton force is going to go this way for rotation. That's a positive moment. See the positive sign in front of the 20. Finally, the 15 kilonewton force is also going to go in a positive or counterclockwise direction. There's a plus sign that's understood here. If you clean this up with some algebra, you'll eventually get RB as 22.5 kilonewtons. Once you substitute RB into this equation, you can see that you get a negative answer for RA. So RB is done. We have 22.5 kilonewtons, but we've got a problem here with RA. And it's not too much of a problem, but it's still something we need to resolve. See, we assumed that RA was going down, but it's negative. So that means that RA must have been going up. So you don't have to write a therefore statement for me, but at least make sure you present the answer by saying that it should have been acting in the upward direction. So, like I said earlier, you draw the diagram wrong. It doesn't destroy the answer. It just means that you might have to do some cleaning up at the end to clean up the small mess that you might have made with the plus and minus signs. And that's it. That's how you do trusses. For this week, I have additional examples on trusses that I'd like to present the answers directly on Blackboard. So for your assignment this week, you don't have to worry too much about this example or the next one, but I would like to give you some time to look them over and to make sure that you understand how to set them up. The full solutions are available with diagrams on Blackboard. Just keep in mind here, A is a pin and B is a roller. In this question, there's a lot more activity in terms of the forces and the moment calculations. So you got to be a bit more careful. And much like the previous example, You cannot exploit symmetry. I think it's safe to say, though, that most likely the reaction forces are acting upward. But even that reaction assumption is not necessary. Just make an assumption if it's up or down, and if it's the wrong sign, you can fix it at the end. Here's another example. This is a truss structure. Maybe it's a cross section in a roof. I like to point out that with trusses, we don't really consider the mass of these elements, so it would be a model, not exactly a representation. So anyway, we have the following downward loads acting at B, C, and D, and this example has a full solution with a free body diagram on Blackboard. So what's on the menu for next time? I'd like to finish off the examples in our notes, and being that it is our last example, I really want to get into some advanced questions involving trusses. And since we have not discussed beams in any detail beyond the simplistic ones we saw last time, lots of beams next time. So I look forward to our next meeting, and enjoy the video, and take care.